Okay, class, we are going to do section 8.5 on counting principles, and we're also going to talk about what permutations are and combinations. Okay, so here we're going to talk about the difference between with replacement and without replacement. So here we're going to select a pair of numbers at random. We're going to determine how many ways a computer can randomly generate two integers from 1 through 12 whose 6 is sum. So we have the first number and the second number being picked. Okay, so we want the sum to be 6. So of course the numbers can't be bigger than 6. So the first number can be 1. Well, if the first number is 1, then the second number has to be 5 if we want the sum to be 6. The second number can be 2, which means, or the first number can be 2 and the second one being 4, or we can have 3 and the second number can be 3, because with replacement means it's just two integers versus in the second problem distinct integers. Okay, so there is no rule in this first problem that says it can't be 3 and 3. Okay, so both numbers can be 3. The first number can be 4 and the second number can be 2, and the first number can be 5 and the second number can be 1. The first number, if that's 6, this would have to be 0, but the numbers are 1 through 12, which means we can't have that. These are all the possible options. So we have 1, 2, 3, 4, 5 different possible ways where the computer can generate two integers from 1 through 12 whose sum is 6. In the second problem, we want distinct integers whose sum is 10. So we have the first number and the second number. Okay, so we want the sum to be 10, and the numbers are between 1 and 12. So the first number can be 1, and the second would have to be 9 to have a sum of 2, and then 2 and 8, 3 and 7, 4 and 6, 5 and 5, but those aren't distinct, so that doesn't count. The first number can be 6, second number is 4, 7 and 3, 8 and 2, 9 and 1, 10 and 0, well 0 is not one of the possible numbers, so that's not a possibility, and neither are the other ones. So there are 1, 2, 3, 4, 5, 6, 7, 8 possible ways for the computer to randomly generate two distinct integers whose sum is 10. Okay, the fundamental counting principle says that if E1 is the first event, E2 is the second event, and E1, so the first event can occur M times, and the second event can occur M2 times, then the number of ways that the two events occur is M1 times M2, which just means we're going to multiply. So if we can find the number of ways for this thing to happen and the number of ways for that thing to happen, the number of ways for this and this to happen, we would multiply it. Okay, and then if you had 3 things, it'd be M1, M2, M3. Okay, so a combination lock will open when the right choice of numbers from 1 to 30 inclusive is selected. Inclusive means 30 is one of the possibilities versus 1 through 29. How many different combinations? So the different events is, here we have the first number, and we have the second number, and then the third number. Okay, so these are the different events. The event would be picking the first number. The second event would be getting the second number, and the third event would be getting the third number. So how many possible ways are there to get the first number? Well, there's 30 numbers that could be the first number. And since this would be like the event would be that, this would be my M, the number of ways for that event to occur. So there's 30 ways to get the first number, and I'm going to multiply it, all these numbers using the fundamental counting principle. The second event would be picking the second number, and how many ways can we pick the second number? Well, it can be any of the 30 numbers, and it can be a repeat, so it can be 30 times 30, which is 27,000 different 3-number lock combinations are there, assuming you can repeat numbers, which you could have a lock that is 1, 1, 1. It wouldn't be very safe, but you could pick it. You can have repeated numbers. Okay, and 4, it says, in a certain state, each automobile license plate consists of 2 letters. So I have a letter, and then I have a letter, followed by 4-digit number. Number, 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 and number. And there are 26 ways to pick the first letter. There's 26 different letters in the alphabet. And it doesn't say anything. It says how many distinct license plates, but it doesn't say that the letters have to be distinct. So I have 26 choices for the second letter. And the number, well, there's 10 numbers or 10 digits, 0 through 9, 10 digits, 10 digits, and 10 digits. And I multiply it all using the fundamental counting principle, and that's 6,760,000 different license plates. And this would be an example of permutations because order matters. The license plate AB1234 is different than license plates AB4321. The order in which they matters. Okay, so a permutation of n different elements is an ordering of the elements that one element is first, the second one is second, the third, and so on. And it's given by n factorial. So in how many ways can 8 children line up in a row? Well, one way to think about it is you have your 8 children. Okay, so here's the spots for the 8 children. And you have your kids standing over here in the circle. In this first spot, you have 8 of these kids to pick to go in that first spot. Well, now that you've placed the first one, there's 7 kids left there to put in the second spot. And now there's 6 kids. 5, 4, 3, 2. Did I miscount? 8 kids. 1, 2, 3, 4, 5, 6, 7, 8th kid. Okay, which is just 8 factorial. Or 40,320 ways for 8 kids to line up. Okay, so when you have a permutation, and order matters, you put lines out representing the different spaces. In this case, the spot for the first kid, the spot for the second kid. There's 8 kids to put in the first spot. Now that that person's picked, there's 7 kids left to put in the second spot. Then there's 6 kids left to put in the third spot, and all the way down to 1. Okay, so permutations of n elements take an r at a time. So the previous problem, there's 8 kids, we lined up all 8 kids. But what if there's 8 kids and we only want to line up 5 of them? How many ways can we do that? Well, there's a formula for this. It's called NPR. It's permutations of n objects, 5 at a time. If there was 8 kids and you wanted to select 5 of them at a time. And this is when order matters, when ABC is different from the set BAC, because being first in line is different than being second in the line, of course. Okay, so here we have a coin club that has 5 members. And how many ways can you have a president, a vice president, select from its members? Okay, so here it's kind of like lining up, where the first person in line would have the title president and the second person in line would have the title vice president. So if you're having titles, or if coming in first place and second place is different, then order is going to matter. So method 1 would be no formula. So we're going to have the president and the vice president. Okay, there's 5 members. Of these 5 members, how many ways can we pick a president? Well, any 5 of those kids can be president. Times it. Well, the president and the vice president are, of course, 2 different people. So there's only 4 people left to be the vice president. So that's 20. So whenever you have titles like president, vice president, or first person line, second person line, third person line, then you can just have these little bars representing the events and count the number of people or things to fill those events. Method 2 would be using the formula. You have 5 people and we want to know how many permutations of 2 can there be. So with this, just plugging it into the formula, that's 5 factorial over 5 minus 2 factorial, which is 5 times 4 times 3 times 2 times 1 over 3 factorial, 3, 2, 1. Those cancel off with 5 times 4, which is what we had, or 20. So it's really just the same thing. So combinations is when order does not matter, and that's when ABC is the same as BAC. That's an example of, there's 20 people in the room, 3 of you have to leave because there's too many. And so 3 people leave. It doesn't matter if you're the first, second, or third person to leave. You're just part of the group leaving. Okay? So for a number of combinations, if you have 20 people in the room and 3 are leaving, this would be how you fill it out. Okay? So here, first problem says, all right, problem 7. You want to select a committee of 3 people from a group of 20. How many ways can this be done? So order does not matter in this one because you're just having a committee of 3 people. So order does not matter. If these 3 people forming the committee had titles, like in the coin club problem, then order would matter, and then it would be a permutation. But if you're just selecting a committee and they don't have any titles, then it's just a combination. So we have 20, and we're going to choose 3 of them, which is 20 factorial over 3 factorial over 20 minus 3, or 17 factorial. 20 factorial is 20 times 19 times 18 times 17, all the way down to 1. 3 factorial, 3, 2, 1. 17 factorial is 17, all the way down to 1. Those cancel. 6 goes into 18 3 times. So then you have 20 times 19 times 3, which is 1140. You could, of course, take this, plug it into your calculator, as I showed you on the previous slide, and get this number out. And you would have your calculator for a problem like this. Okay, number 8. In a standard deck of cards, if order isn't important, so you're told, so it's going to be a combination, how many 7-card hands are possible? Well, in a standard deck of cards, you should know that there's 52 cards in a deck. So there are 52, choose 7, or plug it into your calculator. So to do it on your calculator, you need to press 52, and then the math button. And then you arrow over 3 times to PRB, to probability, and then choose option 3. So now on your screen, it should say 52 NCR, and this is where you put in 7, and then you press enter. And you should get out 133,784,560. Okay, so in a standard deck of cards, there are 133 million 7-card hands out there. And a 7-card hand would be you being dealt 7 cards and you have 7 cards in your hand. Okay, in a 5-card hand, so now you're dealt out 5 cards and you have 5 cards in your hand. How many ways can you get 4 aces and 1 other cards? So let's talk about getting 4 aces. That's your first event. And then the other event is 1 other card, which is not an ace. Okay, so we're going to figure out the number of ways you can get 4 aces and the number of ways to get 1 other card, and we're going to multiply it using the fundamental counting principle. So 4 aces. How many aces are in the deck? Well, there's 4, and we are going to choose all 4 of them. Order doesn't matter. You're being dealt cards in your hand. It didn't matter if it was the first one in your hand or the second one in your hand. You just got all 4 of those aces. You can also think of it as there's 4 aces. How many ways can you get all 4 aces? Well, one way, by getting all 4 aces. And 4 choose 4, when you plug it into the formula, is also 1. Okay, so 4 choose 4 is 1, and also there's only one way to get all 4 aces, which is the way of getting all 4 aces. And we're going to multiply this by getting 1 other card. Well, how many non-ace cards are there in the deck? If there's 52 cards in the deck and 4 aces, there's 48 other cards. We're going to choose 1 of them. If there's 48 other cards, how many ways can you get 1 of them? Well, there are 48 ways to get 1 other card. You can get the 2 of hearts, 2 of diamonds, 2 of spades, 2 of clubs, 3 of hearts, 3 of diamonds, 3 of clubs, 3 of spades, all the way up through the kings. There's 48 other cards to choose from. So there are just 48 hands, 1 times 48, ways you can get 4 aces and 1 other card. Okay, well that is all, and I will see you all in the class.